Okay. So it's really a pleasure to be in India for the first time in this beautiful place, and it's an honor to be invited to give these lectures. And thanks to start with to the organizers for putting this huge task together. Okay, so my goal is to deliver some kind of overview set of lectures about complex analysis and complex analytic geometry. And I provided a set of notes which are sort of will be in progress until the end of the course and beyond. And the idea is that you can really dig in to the details looking at the notes, but the lectures should give you a kind of warm-up. So especially in the beginning, I'm going to be covering very elementary material. I was told roughly what the makeup of the audience was going to be, but the beginning is certainly more elementary on some level. It's really background material about complex manifolds and the basic objects of the kind of complex geometry that goes into studying the Cauchy-Riemann equations. So I'm going to start at the very beginning, so I apologize to people who know this, and if everybody knows this, then you could just start yelling at me and I can move ahead. Okay, so I want to start with talking quickly about complex manifolds. So implicitly, I assume that you know what real manifolds are, and so so a complex manifold of dimension n, so this is its complex dimension, is a real 2n dimensional manifold with a holomorphic atlas. That means that it's covered by a collection of open sets, and on the intersections of those, well, those open sets are all homeomorphic to subsets of R2n, which you identify with Cn, and on the parts of those open sets that belong to two different charts, there's a mapping from one open set to the other. Well, it's the same set, but seen in different charts, and that map should be holomorphic. So that's roughly it. And what that tells you is that any local calculation that you do in complex analysis makes sense in some global way on the manifold. So the background for several complex variables, Debraj will give a kind of short course on that, if I understand correctly. So I'll leave things like the definition of holomorphic maps to that. But I think you probably all know it. So let me give a few examples. So of course, a complex vector space is a complex manifold. So the way you get a map to Cn is you just choose a basis, and that gives you a homeomorphism from this vector space to Cn. And so there's only one chart, so there's nothing to check about the atlas being holomorphic. So okay, so this will be the first example. Maybe before I go on to the second example, let me say what I call a complex submanifold. A complex submanifold, say y in X is a subset such that in every coordinate system U. So this is one of these open subsets in the atlas. The set U intersection Y is equal to the zero set, the common zero locus of, say, K functions. So here F1 through Fk will be holomorphic functions on U, and then we'll ask that df1 wedge dfk is nowhere zero on the intersection of y with u. So this just means that these differentials are independent vectors at every point where the functions themselves vanish. This is not the only possible definition of a complex submanifold, but this one has the advantage that it's a closed subset. Other kinds of complex manifolds you can get by looking, for example, at a holomorphic differential equation. You can follow its integral curves, and that will give you some submanifold, but that can kind of come back and wrap around and get closer and closer to itself. And so it's not going to be defined exactly as the zero set of some holomorphic functions. It'll be contained in something like that, but it's not going to be defined exactly in that way. So I'm sticking to this as my definition, but of course you construct what you need. So with this definition of a complex submanifold, complex submanifolds are also examples of complex manifolds. So to do that, you have to use the implicit function theorem, and that's the purpose of this condition here. But so building off that for this example here, you could look at, so you can look, for example, at complex submanifolds of Cn. So that's not really it's not much of an example. It's very general. But you can make it slightly less general by taking, of the form, say, F1 equals Fk equals 0, where now these Fi are holomorphic on all of Cn. So, and then of course you need this condition as well. Nowhere 0 on, let's call this thing Y. So these manifolds are special. They're globally cut out by a choice of exactly the right number of holomorphic functions. This condition says that they're exactly the right number. But you can have complex submanifolds of Cn which are not cut out by global functions like this. So these are called complete intersections. These are just all possible submanifolds of Cn. And if we get time to cover it, we'll discuss those later. Those are turn out to be manifolds called Stein manifolds. The definition of Stein manifolds comes more naturally from complex analysis, but there's a famous theorem of R. Narasimhan that says that they're actually the same as closed submanifolds of Cn. Okay, maybe some more concrete examples. The ones that are not submanifolds of Cn. So for example, you can take C, and then you can take the one-point compactification. So you add a single point, which you call infinity, and the topology of this thing is that the open subsets are all open subsets of C, or else the complements of compact sets in the one-point compactification. So this is sometimes called the extended complex plane. And so you can cover it by two charts. You can cover it by C. This is one open set. And then the other one is, so let's call this manifold X. So X minus, say, the origin inside C. We could take any point, but the origin is fine. And then the map that sends you, that sends this part to C is just the identity map. But for this one here, you have to do a little bit of careful work. So you look at the map that inverts the complex variable. And that's, of course, not defined at infinity, because we don't know how things are defined at infinity. But by the Riemann removable singularities theorem, if you're going to make it holomorphic, there's only one thing you can do, which is make it vanish at infinity. And then you check that the transition map is exactly the map that inverts the variable, which is a holomorphic map. So so let's say if we have our complex vector space V, we can take the projectivization of V. So this is the set of all one complex dimensional subspaces of V. So this is also a complex manifold. So let's say if the dimension of V is n plus 1, here's how you can construct charts. You can do it less specifically than this, but this is maybe the quickest way to discuss it. Let's choose a basis, E0 up to En, a basis for V, and then let's take Z0 up to Zn to be the dual basis of the dual vector space V star, set of linear functionals on V. And so you can define the set Uj, which is the set of all points, set of all one-dimensional subspaces L in P of V, such that so Zj of L is not equal to 0. So any, it's L minus 0. Sorry, Zj, I guess I could say it like this. Not equal to 0, so for some point V in L. Of course, at the origin, it's going to always be 0, because the linear functional at the origin is 0. But any other point, it's either always 0 or never 0. So, so these things, this dual basis for V star gives us things on the projective space called homogeneous coordinates. So they identify, so you can identify points of P of V with points, say Z0 up to Zn. So these would be equivalence classes of points where 2 points are equivalent if one is a scalar multiple of the other. Maybe I shouldn't write it this way. This is Pn, or sometimes written P of Cn. So you can always make this vector space standard. We'll be using this example later when we talk about things like how to embed compact complex manifolds in projective space when you can do that. That would be one of our applications of the D-bar equation. Now, you can also go on to discuss projective submanifolds. So there, the condition is not quite like this, because there are no holomorphic functions on these projective manifolds because they're compact. But if you have a submanifold of projective space or a subset of projective space, then you can look at the set of all points in the vector space V so that the line through the origin passing through that point is a point in your subspace. In other words, you have a map from V minus the origin to P of V, and you can look at the inverse image of that map. And if you want to check whether or not a subset is a projective manifold, it's equivalent to being a submanifold of V minus the origin. It's not V, but V minus the origin. So anyway, I just thought I would mention it, but I'm not going to go into details for this example. Okay, so let's call this part A. So the next thing I want to talk about is holomorphic vector bundles. So there's a standard definition of holomorphic vector bundles, and I was trying to be clever and shorten it, but the shortening is not quite right. So it's missing a couple of hypotheses, which the updated notes will have the missing hypotheses. But Pranav pointed this out to me last night, but I'll just add them in the lecture as well. So, okay. So a holomorphic vector bundle is a triple. So it's a bit redundant to say a triple, but let me say there's a total space V that's a complex manifold. Then there's a base space X, which is also a complex manifold, and then the third thing is a map pi, which is holomorphic, and then you need some properties. So the first thing you need, you really just need two things, the way I'm stating it here. So you want to say that the fibers of pi are endowed with structures of vector spaces. This is one. So this was implicit in what I said, but I didn't say it. But the missing thing is coming now. So for which the scalar multiplication and addition are holomorphic maps. So the first one is a map from V to V, and the second one is a map not quite from V cross V. This is the direct sum of vector bundles. So what it means is that the fiber over a point X is the Cartesian product of the two fibers, or the direct sum if you prefer thinking about abelian groups. So you should get holomorphic maps. This one should be C cross. The scalar is in C. And then the second thing is local triviality. So this is called local triviality. So it means, so there exist maps from, actually this is not precise. So for every point P in X, there exists an open set U in X, which contains P, such that P is in U. And holomorphic maps E1 up to ER, say from U into V, such that A, so pi of EI of X equals X for all X and U, and B, the span, so C E1 of X plus C ER of X is equal to the vector space Vx, which is by definition the fiber of pi. In other words, you can choose a sort of a family of bases that vary holomorphically for the vector bundle. So that's called a frame. And this choice of basis is not unique. If you choose another one, then of course you can express the new basis in terms of the old basis in a linear dependence, and so there'll be a linear transformation which is invertible, but it also depends on the point in the base holomorphically. So those things are called transition functions, and you can also write down a definition of a holomorphic vector bundle in terms of transition functions or in terms of a third thing, which is a trivial vector bundle, which is glued together by transition functions. So, right. Okay, so I won't bother saying too much about that. That's something you can get into, or maybe we can discuss in the recitations for people who haven't seen the concept before. So this number R, is called the rank of the vector bundle V. And the last thing we need is to decide which vector bundles are different. So so a vector bundle map is a holomorphic map, say from V into W. V and W are vector bundles, so this would be a holomorphic map, and then you have projections so these are for vector bundles over the same base. This map should be sitting over the identity. So what this means simply is that F is, well, so far what it means is that F is a holomorphic map which maps a fiber of V over X to the fiber of W over X. But we also want more than just holomorphicity. We want this to be, which is linear on fibers. So one way to think of vector bundles is really as a vector space that depends on a parameter. And so a vector bundle map is a linear map of the vector space that also depends on the parameter. So you should sort of think of the coefficients of the matrix as being functions rather than numbers. And so you say two vector bundles are isomorphic if there exists, so F, say from V into W, a vector bundle map, and G from W into V, such that F composed with G is the identity map for W, and G composed with F is the identity map for V. So it's kind of a logic thing why you want to introduce this notion. So for me, I always thought of I'm not really a logician, so I always thought of a vector bundle as something determined only up to isomorphism. But when you start talking, for example, about the moduli, the parameters that define all the vector bundles, that definition runs you into trouble. So you have to identify two vector bundles if they're isomorphic. But we're not going to worry too much about it, but it's something you have to be aware of if you read, for example, papers in algebraic geometry. They define moduli as vector bundles modulo isomorphism. Okay, so some examples of vector bundles. Is it okay? I mean, I know that the line is supposed to be there, but everybody on the other side is okay if I write this far down, especially down below? Okay. So, maybe one other thing to remark here. For almost everything we're going to do with vector bundles is going to involve the rank 1 case. But there's one exception which is going to appear everywhere, which is when we study differential forms, we will often have to think of them as sections of a vector bundle, and that would only be one-dimensional in very special cases, if the underlying manifold were one-dimensional and we considered certain types of forms. So we really do make use of vector bundles, but in terms of the complex analytic content, the most important case will be line bundles. So that's when R is 1. Rank 1 are called line bundles. Okay, so again, you start with a completely useless example, which is trivial bundles. So that means you have a vector space V naught crossed with the complex manifold, and the map pi is just a projection to the second factor. But in a sense, all vector bundles are locally like this one by their very definition. And then continuing with the useless examples, it's getting to be a tradition. If you've got two vector bundles, so far we only have one, but if you've got two of them, say V and W, you can make new ones. So, for example, you can take the dual vector bundle. So that means that the fibers are just the dual vector spaces. The dual vector space is always isomorphic to the vector space itself, and at least in finite dimensions, which is really the only case we're going to formally deal with. But the important thing is that there's no canonical isomorphism between a vector space and its dual. You have to make some kind of choice. And the point here is that these vector spaces are not completely free to express their vector spaceness in any way they wish. They have to be very friendly with the vector spaces next to them because they're varying holomorphically. And so it's important to think of this dual bundle not as the previous vector bundle. In fact, we'll see later that they're really quite different. They have different holomorphic properties. But as far as the fibers go, it's productive to think of it really as a set of linear transformations on the vector space and not to choose a basis and identify it with a dual. Okay, so there's V star. You can also form something I alluded to before, the direct sum, at V and W. So this is, as I said before, the fiber over a point X is just the direct sum of the vector spaces Vx and Wx. And you can form other kinds of bundles, like you can take the tensor product or the wedge product, which is formally like the tensor product. It's a quotient of it. So it's a skew-symmetric pairing. That's really more relevant when V equals W. So. Maybe one other useful example. If you have a map F from X to Y, where these are complex manifolds, and then you have a vector bundle V over Y, then you can define the pullback as a vector bundle over X. So this is it's a kind of common construction. It's the set of all x and v such that, so x is a point in x, and v is in the fiber over the image of x. So this is a subset of x cross v. And this subset, I write it this way because in my notes I gave as an example the blow-up of a complex manifold, but Vamsi Pingali pointed out to me that I don't use it later and it's maybe a bit heavy. So I left it out, but if you read the example, you'll see this kind of relation appearing there as well. Okay, so much for abstract things. So the next example is still fairly general. Okay, so let's let X be a complex manifold. What I'm going to define here is the holomorphic tangent space. Let me get another piece of chalk. Okay, so let's define. So I'm going to assume that you know what the real tangent space is, or the real tangent bundle. So let's define a vector bundle map from the real tangent bundle to itself, and it's defined as follows. Okay, so this X is a complex manifold, so that means that locally we can have some local coordinate system. So let Z equal to Z1 up to Zn be this holomorphic coordinate system. And let's write this Zi in terms of its real and imaginary parts. Okay, so then what I'm going to do is look at the tangent vector d by dxi, and I'm going to apply j to that. And the definition, this is how I'm going to define j. J of this vector will be d by dyi, and then j of d by dyi is a negative d by dxi. So this is linear map defined on the fibers of Tx in terms of a holomorphic coordinate system. And now I'm going to make this claim that this map is independent of the choice of the holomorphic coordinate system. Meaning if you chose another coordinate system, W, and you wrote Wi as ui plus square root of minus 1 vi, then you could express d by dui in terms of d by dxi and d by dyi, and similarly for d by dvi. And if you use this rule J for those new vectors, applied linearity, you would get exactly the same formula, but in terms of u's and v's instead of x's and y's. So that's an exercise. Show this is independent of holomorphic coordinate chart. Okay. All right, so then Well, if you've thought about these real linear transformations that do this, they're just in a direction of in a given complex line, they're just rotation by 90 degrees. So that's supposed to imitate multiplication by the square root of -1. And so you would like it to be literally multiplication by the square root of -1. But in order to do that, you have to do a little bit of finessing. So, I mean, if it's really multiplication by some number, then we should try to diagonalize this operator. So try to diagonalize J. So the first thing you want to do is look at what are the eigenvalues. And so if you apply J twice, you get minus the identity. So that shows you that the eigenvalues, there's only two eigenvalues, and they're plus or minus the square root of -1. So you cannot diagonalize this operator on Tx. But the usual thing we do in our linear algebra classes is that you work with complex coefficients instead of real coefficients. So you look at Tx tensor C, and then you diagonalize this operator there, and what you find is that it's a direct sum of two isomorphic vector bundles, real vector bundles. So this T10 of x will be the span of 1/2, this is a normalization, so let's see if I did this right. So if I apply J to this, so J of this will be 1/2 d by dy I minus square root of -1 d by dxi, which is square root of -1 oh, thank you. This one's okay. J. This is plus. Thank goodness. Okay, so this is 1/2 d by dxi minus square root of -1 d by dyi. So that's indeed the eigenvalue, the eigenvector with eigenvalue square root of -1. So this is E of E sub j of square root of -1. And the other one is the corresponding eigenspace with eigenvalue negative square root of -1. But it's actually just a complex conjugate vector space. So okay, so what you see is that T10x is a holomorphic vector bundle. So how do you see that? Well, these vectors, they're given a name in your complex analysis class. I think Werdinger was the first to introduce them. These are called the Werdinger derivatives, and they transform by holomorphic transformation laws. So if you apply the chain rule with the holomorphic change of coordinates, you'll have a holomorphic transformation law. So from this, you have this local triviality, and you can build, you can check all the definitions. So the fact that they transform holomorphically tells you that these two conditions in part 1 here are satisfied. So. Okay. Something that's useful to know, but I'm not sure we're really going to need it a lot. I might as well mention it. So you can look at this original real tangent bundle, and that you can embed into the complexification as the real subspace. So it's just a set of real vectors in this complex vector space. And then this we just saw is isomorphic to T10 plus T01. And then you can just project to the first factor. So I claim that this map here, let me call it S10, this is an isomorphism. In fact, you can check that this S10 inverse is just twice the real part of this complex vector. And this isomorphism is particularly important because if you take one of these complex vectors and act on a holomorphic function as a directional derivative, you'll get the same thing as if you take twice the real part of that vector. And that's one of these features of the Cauchy-Riemann equations, that you can take a limit in any direction that you want to compute the derivatives. So it's kind of a nice way to identify this holomorphic vector bundle with this real vector bundle in such a way that preserves the action on holomorphic functions. It puts a structure of a holomorphic vector bundle on this, on Tx itself. Okay, so I said before that we're going to have a lot of line bundles in the picture. So I want to give some examples of line bundles that are going to be important for us. So the first, I'll say some important line bundles. The first one is called the canonical bundle. Okay, so you can take this T10 of X and take its dual bundle. So this T10 is the sections are these kind of complex vectors. So the duals will be complex valued differential one forms of certain type. We'll discuss in a little bit. But anyway, it's some dual bundle. And then you can take the determinant of this. And that's called the canonical bundle. So it just means, okay, so let me be a bit more explicit. So here we had this, given a holomorphic coordinate system, we got these vectors d by dzj, and the corresponding dual frame here is denoted, say, dz1 up to dzn. And so taking the determinant means you look at the line bundle, which is just multiples of dz1 wedged, all the dzi's wedged together in this order. So this is the thing that gives you the frame, and the holomorphic structure follows again from, well, anyway. Okay, so, I mean, the nice thing about these, this vector bundle, well, it'll appear many, many times. One of the things you can do is integrate the squares of sections of this bundle. This is a kind of Hermitian square root of a Lebesgue measure. Right? If you take this and wedge it with its complex conjugate and multiply by the correct unimodular constant, you'll get the Lebesgue measure up to certain normalization. So, and any section of this bundle will be some function times this thing. So if you take the square of that section, you can integrate that. It's a measure. So I'll cover that again later. That's why these line bundles are important. And the name canonical comes from the fact that this is really the only non-trivial line bundle that every complex manifold has. So you often have no other, if you want to study complex manifolds in general, you often have no other line bundle besides this and the trivial bundle to really look at. So, okay, so that's still too general. Let's be only slightly less general. Okay, so let's let X be a complex manifold, and let's let Z in X be a complex submanifold of complex codimension 1. So what does that mean? So for every point P in X, there exists a neighborhood U, open set with P and U, and a holomorphic function F in O of U, such that Z intersection U is exactly the zero set of F, and so dF restricted to Z is nowhere zero. Right, that's our definition of complex submanifold. The only thing here is that there's only one function that cuts out the submanifold. Okay, so now let's actually be a bit more specific and specify the neighborhood as well. So now suppose you take your complex manifold X, so say let U alpha be an open cover of X, and then you have functions F alpha, which are these F U alpha, as just specified. So these are functions which, in the neighborhood U alpha, they cut out Z. So their zero set is exactly the set Z with the correct multiplicity because dF doesn't vanish on the zero set of F. Okay, so then you can look at the function F alpha divided by F beta. So this is going to be a holomorphic function on U alpha intersect U beta, but it's actually better than a holomorphic function. It has no zeros and no poles, because its zero set is exactly Z counting multiplicity. So this is GL1C. I guess it's O. Oh, well, it's not what I mean. So it takes values in GL1C. So it's a holomorphic map from this intersection to GL1C. That's what I meant to say. So we can call this G alpha beta, and these G alpha beta obviously satisfy G alpha beta, G beta gamma, G gamma alpha equals 1, and also G alpha alpha equals 1. So for all alpha and beta and gamma, this is true, and this is the information you need to glue together a line bundle from these transition functions. So thus, we have a line bundle LZ over X, but we also have some additional information. We have a section of this line bundle. So how do we have a section? Well, it's just you do this cross multiplication. So you can write F alpha as G alpha beta F beta. That means that these local functions piece together to give you a section of this line bundle. So let's call it F, whose zero set is exactly Z. So this line bundle will play an important role when we study the L2 extension theorem towards the end of the course. Okay, so this is the first example. This is the second example. Okay, so let's do another example. All these things are very general. We'd like to have at least one non-trivial example of a line bundle, which is not completely general. So, unfortunately, it's tautological. Yeah, question. I'm not. So you can construct this line bundle in general. But what I'm going to do, I'll give you a kind of, preliminary answer. So what I'm actually going to be interested in doing is extending differential forms of top degree from some submanifold to the ambient space. But the top degree changes, and I'd like to know how it changes. So if I assume that this thing is smooth, then the differential of this section, which is something that doesn't make sense in general, will be well defined on the zero locus of F, but also it will provide a nowhere vanishing section of the conormal bundle of Z tensored with this line bundle. So in other words, this line bundle, when this Z is smooth, this line bundle is actually a holomorphic extension of the normal bundle of Z to a holomorphic line bundle over all of X. So that's the relevant feature. I'll be saying that again later for those of you who didn't understand what I said. Okay, right, so I want to give an example of a non-trivial example, but unfortunately tautological example of a holomorphic line bundle. Yeah? G alpha beta? It's a quotient of two holomorphic functions whose zero set is exactly the same counting multiplicity. Right? They both vanish on Z, exactly on Z, and their differential doesn't vanish there. So if you really wanted to give a rigorous proof, you probably have to do the Weierstrass preparation or implicit function theorem or something like that. But at least morally speaking, that's the reason. Okay. Yeah, the tautological bundle. Okay, so let's start with Cn. Actually, you can start with, or Cn plus 1. You can start with any vector space. It doesn't have to have coordinates, but let's, for the sake of visualizing, let's assume we have a coordinate system for now. We would need a basis eventually, but not right now. Okay, so remember we defined the projective space. So Pn is just the set of lines through the origin in Cn plus 1. So every point of Pn is a line through the origin. So in particular, it's a complex line. Right? So that defines a line bundle. Like every point is actually a line. So this is called sometimes called the universal, sometimes called the tautological line bundle. So that doesn't feel like a real example, but let's talk about the dual bundle. That's more important, actually. So okay, so here's Cn plus 1, and then you have a typical line, L, one-dimensional subspace. And then you want to look at the linear functionals on this line, right? Is that for me? Oh, am I limited to 1 hour even though we started early? Or it came from this alarm. Okay, anyhow. Okay, all right. Okay, so we want to study the dual bundle, so that's called the hyperplane bundle. So this is U dual. So remember I said you want to look at the linear functionals on this line. So a linear functional on a one-dimensional subspace is always the restriction of some linear functional on the whole space. Okay? So in fact, any linear functional will be the restriction to this line of some linear functional, and conversely, given a linear functional on all of Cn plus 1, you get a point in the fiber of this line bundle here. So in particular, this means that the Cn plus 1 set of linear functionals contained in the set of holomorphic sections of this line bundle. So in fact, it's equal. But that's something, I can't remember if I gave it as an exercise or not, but it's something we can talk about in the recitation for those who want to know. And then there's an interesting corollary of this, which is that this line bundle actually has no non-zero holomorphic sections. Corollary. So let me give a notation. So this will be, I'll use the notation gamma O of Pn H. So holomorphic sections over the base manifold of the line bundle or vector bundle. So the claim is that for the dual bundle, there's only one holomorphic section of this, which is just the zero section. Okay, so how do you see that? So when you have a line bundle and its dual bundle, you can make a holomorphic function on the base. So let's say, let's let sigma be one of these sections. We're trying to prove that it's zero. Okay. And let's let lambda be in Cn plus 1 dual. So that we know is a holomorphic section of the dual bundle. So they're dual bundles, so I can pair them together. So I can apply lambda to sigma, and then I get a function which is holomorphic on the base. So it's just assigning a number to every point on the base, holomorphically varying. But this is a compact manifold, so this is just, these are all constant. And so what can happen here? So either this thing is never zero or it's always zero. There's no other choice. But if you have a linear functional on Cn plus 1, it has a kernel. They all have kernels. So any line lying in the hyperplane, which is the kernel, will give you a zero. And so the zero, that means that this thing has a zero somewhere, and therefore, since it's constant, it must be zero everywhere. But since this lambda is not zero everywhere, this sigma must be zero on an open set. And so by the principle of analytic continuation, sigma has to be identically zero. So, okay. By the way, I mentioned that the kernel of lambda is a hyperplane. So a hyperplane in Cn plus 1, that projects to a submanifold in the projective space of codimension 1. And if you take that as your Z and go through this construction here, then you will recover this line bundle here. which is why it's called the hyperplane bundle. It comes from a projective hyperplane. All right. Okay, I think I have about 4 minutes, so 4 extra minutes. So let me talk quickly about differential forms, and we'll end there. Actually, you know what? Maybe I don't want to rush that. I'll start that in the next lecture. I want to do one more example of a complex manifold, which is one of my favorites. So Pranav's heard me say this at least 3 times. I want to give a non-trivial collection of examples of complex manifolds. So let's let S be an oriented or orientable, let's make it oriented. Let's say we have an orientation surface. And then let's let G be a Riemannian metric on S. So there's a theorem that goes back to Gauss, at least in the real analytic case, and then it was proved by Kohn and Lichtenstein independently. And then it was reproved by Mori, and then it was again reproved by Alfors and either Berling or Bears, maybe Bears, and also by Chern. So this is the theorem on isothermal coordinates. So it says that, so this is a theorem. It says that for all points x and s, there exists a neighborhood U and a map phi from U into R2, which is a diffeomorphism onto its image. So let's say U into V in R2, such that, say, if you take phi inverse and you pull back the metric G, then you get some function times the Euclidean metric. In other words, you can always choose the coordinates so that your metric becomes some function times the Euclidean metric, so conformal to the Euclidean metric. Okay, so now you can cover the whole surface. Each point of the surface you can cover by such a coordinate system. And I claim that the atlas you get, well, there's one other thing I'm going to add. So of course you can interchange x and y and you still have such a coordinate system. But since our surface is oriented, we have a choice of which of these we could take, and we take the one that fits the orientation. Okay? So now we have an oriented atlas by coordinate systems which make the metric conformal to the Euclidean metric. And I claim that that's a holomorphic atlas. And that's very easy to see. The reason is that the transition functions for these coordinate systems, they map the Euclidean metric to a multiple of the Euclidean metric as well. That means they map circles to circles, and those are holomorphic functions. That characterizes holomorphicity. So whenever you have a surface, as soon as you choose a Riemannian metric, you define a unique complex structure on it. The correspondence is not one-to-one, but it's almost. If you replace the metric by a conformal metric to that, in other words, a function times that metric, then you get the same complex structure. So the conformal classes of metrics give you exactly all the complex structures on an oriented surface. When the surface is compact, you can say a lot about this collection of things. When it's non-compact, you can still say a fair amount, but in the compact case, it's a finite dimensional space. If the genus is 2 or more, then the dimension is 6G minus 6. In the non-compact case, it's an infinite dimensional space, but you still have a lot of information about it. So. Okay, so let me stop here.